Welcome to day 2 of the Waves and Sound unit. Hope you enjoyed the first one, in which we kind of had an intro to waves and looked at just defining the characteristics. Today we are going to look at relationships between characteristics, and understanding some of these ideas is really a big idea in the study of waves. Ultimately, we're going to use that discussion to derive the wave speed equation, which is the big equation on your equation sheet, and then have a brief discussion about wave energy. Just so people know about some of the mechanics of the course, for homework, every time a homework is assigned, I will accompany it with a discussion thread, any questions you have about the homework, and that'll just kind of be open while people are doing the homework. The next day, or before the next day, or kind of when you complete the homework, you should use the submission module for the date of the homework. It should be labeled, and submit a picture or a PDF of your hand-worked solutions. So if there's any questions on that, please do email me and we'll figure out how to get it done. So this is just going to kind of start by detailing an experiment I used to do in AP Physics 1 and that we used to do actually in general physics. It ended up taking a long time, but it's an amazing activity. I'm just kind of going to run through the results today. So what we did is we used a wave machine. What is that? I'll show you. To create many different periodic or continuous waves, and you know what that is based off of yesterday's discussion, not pulse waves, on a wave machine, and then measured the wave characteristics for each. And we would do that with video analysis within Logger Pro, and then ask the question, if we plotted the relationships on a graph, could we find mathematical relationships between them? Or in some cases, a lack of mathematical relationships between them. That could be interesting too. So this is what a wave machine looks like. It's a series of connected oscillators, which you know, and so when this one is wiggled up and down or oscillated or vibrated, the actual disturbance itself propagates along this direction. Now people really like that. It's a pretty cool thing to watch, but what we did here is in a number, so in this particular one, the source, which is basically this hand here, sort of picks an amplitude or frequency and then just kind of sends the wave along. And then this is a different one, done at a different amplitude and or frequency. So then with this series of videos, we would kind of insert the movie into Logger Pro. We do some things here. We could set the origin along here so that, maybe this represents a 0 position. We could allow this thing to start sort of progressing. We'd set a scale. Maybe this whole thing is like a meter long. I actually have no idea how long it is. And then what you could do is you can kind of like put a point here. We could measure photo distances from, say here to here, where that might represent close to the amplitude, and then sort of progress this thing, later, and we could see that this initial crest is now over here. We could look at these two and measure a wavelength, but these are all things that we would do, and then for each of these labs we compile or we'd collect all 5 characteristics on each wave and then just kind of put them all together to see if, as we change different things, was there any relationship between them. And then we would have everybody pool their data, and these would be like the 15 different waves that people had analyzed. And so we wanted to kind of graph all of these versus each other. So it's pretty neat. The first thing we want to maybe ask, because we think there should be a very predictable relationship here, is No, not the relationship between frequency and frequency, even though I know this is shocking. But like the relationship between frequency and period. And if we auto-scaled this thing, kind of what does that look like? Well, it certainly looks like an inverse relationship. We could go ahead and put a power fit on there. It is not shocking that the power emerges as -1, meaning this is an inverse relationship. Not to mention, the coefficient emerges as basically 1. What this is saying is f equals 1 times t to the -1, or f is the inverse of period. That's good news because that's the definition of period and or frequency, or the relationship between them. And we would be surprised if it was otherwise, but it's actually this frequency and these periods were measured in 2 different ways, so it's nice to see that we get that relationship. So here's that graph just to summarize our findings, that for the relationship between frequency and period, we discovered that these two were the inverse of each other. They are effectively the same thing. Obviously, they're the inverse, but when anybody's making a comment on frequency, they're making a comment on period, and period on frequency. They're just defined as the inverse. So the only thing about that is when frequency goes up, period goes down, and we saw that with oscillatory motion. And when frequency goes down, the period goes up. A longer period means a lower frequency. A shorter period means a higher frequency. And as you saw from the video and the wave machine from yesterday, we can control period and frequency. If you are the person oscillating the medium, you have control over that. And that's why in the study of waves, we see period and frequency as dependent variables. Excuse me, I said that wrong. We see period and frequency as independent variables, things you can control that may have an effect on other things that depend on them. So what about amplitude? If we try to see how other things are affected by, say, amplitude. That's a weird graph until we kind of auto-scale from 0. This is a real, particularly when you see these other relationships, this is sort of a real mess. And then it doesn't really matter what we put on the axes here, but it looks as though amplitude and wavelength are basically not connected or have no relationship. And then what about period or frequency? It doesn't matter which one you pick here, but if we go with period, we find a very similar thing, that the amplitude and the period just don't seem to be related in any way. And finally, maybe speed. Now this one is really interesting in that it looks like there's something more meaningful here, but this is actually a better comment on speed than it is amplitude, and speed's one of the things we're gonna show in a little bit. But this is kind of a hint to a future result, which is that change in the amplitude doesn't seem to change the speed. So here are the graphs dealing with amplitude. These are really kind of the 2 big ones, even though these 2 actually look really similar and sort of hints at something we'll see later. But amplitude and period, or amplitude and frequency, are both what we might consider independent variables. So amplitude is basically independent of the other characteristics. And we think of amplitude just like we think of frequency or period as an independent variable. The idea that these 2 things, period / frequency and amplitude, are independent variables shouldn't come as any surprise if you remember this wave on the string machine. Wave on a string applet here. And that's because there were 2 different controls for amplitude and frequency. We could adjust amplitude, we could adjust frequency. Any change on this doesn't necessitate a change on this, and I can have high amplitude with high frequency or high amplitude with low frequency. We could combine low amplitude and low frequency, or low amplitude and high frequency. Changing one does not have an effect on the other. They're 2 different things that I can change, and then we might see, and does changing them have an effect on anything else? Both of these would always be proposed as ways to change the speed by people who as you'll see, don't necessarily know much about waves yet. So one of the things you might say is, I'm going to send the wave through the medium faster by really making a big wave or a high amplitude. Or I'm going to try to make the wave travel faster by oscillating this up and down more frequently. And as we'll see from the data, we'll go ahead and look at it now, but that doesn't end up working. We already saw the result for speed versus amplitude. How does speed result from amplitude? Well, it doesn't really change as amplitude changes. So here's, I really make a big wave, same speed. I really make a small wave, same speed. What about period or frequency? I take a long time in between oscillations, high period. I take a short time in between oscillations, low period. This emerges as almost the same exact value. And for this particular case, I could just go kind of through here and say, what is the approximate value? And it looks like the approximate value here is about 0.54. So regardless, on this wave machine, regardless of what we do with period or amplitude, all the waves appear to travel at about 0.55 meters per second. So here are those two graphs. Amplitude doesn't affect speed. Period doesn't affect speed. Therefore, frequency doesn't affect speed. And this is really important. Can wave speed change? Yes, it can. But the thing that produced all these waves traveling at the same exact speed was that they were all in the same medium. And it's the medium that determines the speed of the wave, not the wavelength or frequency. Excuse me, not the frequency or the period or the amplitude. It is not correct to say that speed never changes. Speed changes when something about the medium changes, but you cannot change speed by making bigger waves or making more frequent or less frequent waves. The most important dependent-independent relationship we want to investigate is what goes on here with wavelength versus period. How is the wavelength determined by the period? And so this is a really predictable shape. Even if I said, what power fit is this? It's basically a first power, and I think everybody can see that that is a linear graph. I'll just go with proportional to avoid the small intercept. And I get this mathematical model for the relationship between wavelength and period. This is really nice. It says if I double the period, I double the wavelength. Now, do we have a good feel for that relationship in making waves? So this would be a frequency of 1.5. If I wanted to, I could go out here and check the ruler. And the wavelength that I'm creating here is about 2.5. Now, doubling the period would be halving the frequency. So if I went ahead and put this down to 0.75 and then just kept creating waves, you'll see this kind of change here. The waves keep traveling the same speed, but the less frequent, greater period wave ends up having a wavelength that is twice as long. Because this takes twice as long and the speed doesn't change, you could say this crest gets twice as far before the next one is created. And it is not a coincidence that the coefficient in the linear model is exactly the speed that we measured for every wave. So this is a major finding in our exploration of relationships between variables. The wavelength is directly proportional to the period, and the coefficient or the proportionality constant is the wave speed. This gives us the relationship between wavelength and period. Now, thinking ahead, you know that period is defined as 1 over frequency. So if we put 1 over f in for this, you should be able to predict the wavelength, the relationship between wavelength and frequency, but we'll investigate that graphically right now. So instead of wavelength and period, we will say wavelength and frequency. Probably not surprising given what you just guessed it would be. If I put a model fit on this, power fit, It's almost exactly 1, which is an inverse relationship. To clean it up, I can make it exactly 1. And here we go. This gives us the relationship here. Wavelength is inversely proportional. And again, the proportionality constant is the speed of the waves. Here's a summary of that. And our major finding, which is wavelength is proportional to 1 over frequency, and that the proportionality constant is again the speed. These are the same exact finding, right? If I asked you, given this relationship, what would produce a linear graph? And you would say, I would graph wavelength versus 1 over f. And then the slope would be v. Well, that's this graph exactly. So these are both important relationships. This is a little bit more common. It shows that when the frequency goes up, the wavelength goes down. Doubling the frequency halves the wavelength, as you would get kind of by observing the wave machine or the wave simulator. But the important thing here is that wavelength is a dependent variable, and it depends on the frequency or the period and the speed. If I double both the frequency and the speed, the wavelength does not change, because the crests travel twice as far, but the new crests are created at twice the frequency or twice as often, and the results cancel each other out. An important relationship that just kind of comes up qualitatively, but not really in an equation form, is around wave energy and what characteristic determines wave energy. So if you think about it, the characteristic that determines the energy of a mechanical wave, and this isn't always true for non-mechanical waves, and that's kind of an important distinction as you get into the study of that, maybe in another physics class. But for mechanical waves, the characteristic that determines the energy of the wave is amplitude, which you certainly know from playing in the ocean with big waves. Here comes kind of a bigger wave. It's going to create. It's holding a lot more energy in it. In general, we have a relationship between the two. This is descriptive. It looks mathematical, but it's mostly descriptive here, and that is the energy is proportional to the square of the amplitude. So by this reasoning, an amplitude that is twice as much would have an energy that's 4 times as much, and the derivations of that get pretty mathematical. But the main idea being there that the in an amplitude with a wave of a certain amplitude, you've got the energy would be the sum of all the kinetic and potential, and so the derivations are a little mathy, but that's just kind of a general overview. The other thing really is about speed of a wave, which we sort of left unresolved from the mathematical considerations a minute ago. And how does the medium determine the speed of a wave? If you can't change it with amplitude, you can't change it with period or frequency, what about the wave determines that? And the speed of a wave through a medium depends on how tightly the medium is connected and how massive the medium is, or how hard it is to move. And if you think about it, very similar to the stuff we just saw, related to oscillations, and these are ways to describe the elastic and the inertial properties of the medium. So in the case of, say, sound, the speed of sound in any medium is determined by the square root of the ratio between the bulk modulus, which is, another word for that is elasticity of bulk materials, but that's how connected and how tightly one element of the medium is connected to another. It's kind of like almost a spring constant was the elasticity in our mass on a spring. And then the inertial term would be the density. So if there's more mass per unit volume, it is a more massive, more inertial medium. And having more density or more inertia slows this down. Having more connectivity, elasticity, speeds it up. One of the problems in your homework has a wave on a string, and the wave on the spring is determined a little bit differently, but It has a tension, which is easy to see as the elastic property, and a linear density, or mass per unit length, as the inertial property. This would be like a heavy string. You know about this on the guitar. Like if you make the tension higher, or you can make the linear density of the string greater by, getting a more dense string. That's why there's different strings on the guitar. Just a consideration of units there. If this is the square root of the tension over the linear density, that would be those would be the symbols, the T or Ft divided by mu. Don't get scared like all of a sudden this is the coefficient of friction. This is just the symbol for the linear density. The units for that work out as obviously newtons per kilogram, newtons per kilogram per meter. So the linear density is what's the mass per unit length. If we expand newtons, kilogram meters per second squared, and we see some similarities there, this ends up coming down to square root of meter squared per second squared, which you certainly would know as the speed, or meters per second. So that's how that works out. There is one problem on that. So enjoy the homework and leave any comments on the discussion thread, and we'll see you tomorrow for more.